Hi everyone, today we are going to present our masterclass, how to produce lithium battery cell like this. So in 5 episodes, we are going to describe how to produce lithium battery cell components, how the manufacturing equipment looks like, and which are the process challenges that describe the gigafactories worldwide. So we are going to discuss how to produce these battery cells like Tesla or pouch cell or prismatic cell, even including the blade cells. And we go through each single process technologies and we describe all the challenges. This course can be the right one to allow you to increase your knowledge in lithium battery manufacturing and at the same time be fully prepared for the job interview for all other gigafactories and players if you want to join in the lithium battery manufacturing industry. So stay tuned, subscribe to our channels and enjoy. Okay, now we can start to talk about the anode. The anode, as you can see on the left side of the screen, is a sandwich of thinner copper foil in the middle and then a graphite coating on both sides of the copper foil. Okay. In terms of thickness, the copper foil used is thinner than the aluminum used for the cathode. Usually the thickness right now move from 6 to 12 microns. Okay, so very, very thin. And in terms of coating thickness, we're talking about 30 to 120 microns. Okay, so even the cathode material at the end becomes very, very thick. So from 70 to over 200 microns in terms of thickness. And the coating material is made of graphite. There are two philosophies. One is to use natural graphite. One is to use synthetic graphite. In order to increase the charging speed of the batteries, some players are moving to silicon graphite based anode. Okay, so in the new generation of anode, there is not just graphite, but there is graphite plus silicon. This increase again the charging speed, okay, of each single cell and at the end of the battery pack. The same what we say before about the cathode still valid even for the anode. I mean, very thick anode material cannot be used for cylindrical cell because otherwise we have some problems in the beginning of the winding process. But for sure can be used in prismatic and pouch. There are some exceptions, as always. For example, Tesla is using very thick electrode material in their cylindrical cell. There are some strategy to minimize the risk and to combine thick electrode with the cylindrical cell, but is not for sure easy not to achieve. The same that we told for the same that we said for the cathode still valid even for the anode. So even for the anode, the main KPIs or the main features are represented by the chemical composition, the energy density, the charging rate, working life, value chain, and application. As you can see, the anode represents the second most expensive material in the battery cell, and the anode with the cathode is one of the two materials that give the main properties and main performance to the cell. So how works the anode? Okay, in the beginning seems difficult to understand, but it is really, really easy. I mean, as you know, the graphite structure is
defined by basal plane. So the graphite has a hexagonal, okay, reticulum arranged in a plane. Okay, so the graphite is composed by a stack of plane. Okay, where the atom lay on each plane. So during the charging and discharging of the batteries, the lithium ion moves between the basal plane. Okay, so that means that are not, I mean, the lithium ion are moving, okay, from plane A to plane B. And this increase the volume, okay, of the active material in the anode. And the increasing of volume create many effects inside the battery cell once is working, no? Once is operating. Because if there is no empty volume inside the case of the batteries and the anode during the charging phase is increasing its volume, that means that even the internal pressure increase, okay? So some components in the battery cell during the charging are going to suffer this expansion of the graphite. And later on, we'll explain this topic more in detail. So again, the graphite is made of different basal plane. Each basal plane is composed by a reticulum or a pattern of hexagonal, okay, arrangement of carbon atom, okay. And as mentioned before, we have two types of graphite. One type is the natural graphite, and another type is the synthetic graphite. The natural graphite is have a lower purity grade, okay, but have a higher thermal expansion, okay, compared to the synthetic graphite. And for sure, since it's natural, since have a lower purity grade, has even a worse thermal stability, okay, but have a higher capacity due to the larger anisotropically oriented crystalline domains. This is quite difficult to explain if you don't have some basic of material science. But the anisotropic is the feature of material to have different mechanical and physical properties in different axes. Okay, so anisotropic material have different behavior. Okay, depends on the plane or the direction where we are going to measure, okay, the property. The synthetic graphite is more expensive, okay, have higher carbon footprint, but for sure have a higher performance in terms of stability, okay, and higher performance in terms of thermal expansion. So the thermal expansion is smaller. I would like to spend some words for the higher cost due to the manufacturing process. Synthetic graphite is obtained in a very expensive through a very expensive manufacturing process, because in order to obtain the graphite, usually you can start from carbon coke, okay, and then you need to keep your compounds at very high temperature and very high pressure for several days. When I say very high temperature, I'm talking about 1,000 degrees Celsius degrees, okay. So this for sure will increase the cost, okay, because the energy cost is very high, okay, in the last months, in the last years, and even increase the carbon footprint, okay. The main problem is that compared to the cathode, okay, composition, the graphite is very cheap compared to the cathode, okay. That means that the value of the graphite is quite negligible. So there's no interest to recycle the graphite. And this could be a problem if this graphite is synthetic, because this increase a lot the carbon footprint. Is a minor problem for natural graphite, but at the end, this will have an impact, no, of the overall carbon footprint during the battery life cycle. Anyway, if you check the plots, okay, sorry, okay, reduce even here. If we check the plots, the plot on the bottom side, you can see that the demand for natural graphite is going to increase, okay? But even the demand for synthetic graphite is going to increase. And for sure, the natural graphite will represent the main graphite compounds or the main solution for lithium-ion batteries. I think for lower cost. Okay, and even since the graphite, the way to obtain graphite in natural way is very easy, is the availability is very high. For sure, some people try to compensate some lack of availability with synthetic graphite, but just in case for very technological application or for very technological design, I don't see many reasons to move just to synthetic graphite, at least till there's no interest for the recycling. Okay. Okay, I think we can move to the next. Okay, anode. Right now we can talk about anode market trend. As mentioned before, the trend is to introduce the silicon. Okay, in the anode chemistry. These increase, as mentioned before, the charging time, sorry, the charging speed, sorry, decrease the charging time, increase the charging speed, and even allows to increase the energy density, okay? Since is a very good innovation, okay? And that already some players are using in their batteries. One is Tesla, and you can see some articles in the websites. Many other players are going to adopt, okay, this kind of solution in terms of silicon anode battery. And as you can see, the trend is to have a bigger and bigger, so higher and higher demand of silicon-based anode material in the next years. This because the silicon amount is very, very small, up to 10% in weight basis. And the silicon cost is not high, but the benefits are huge, okay? So this explains the trend to use every year more silicon-based anode material. Right now, we can move to the separator. That is the third most important element of the battery cell. Separator is what we see here, okay? Is the white membrane. This is very, very smooth. There is another one, for example, this one that is very, very porous. For sure, you cannot see the pore by your eyes, but the feeling with your hands, the touch is different. So the separator is a very, very thin film of polymer. Usually is a polypropylene or polyethylene, okay, with the micropores. Again, as we've done for anode and cathode, on the left side, you can see a SEM microscope picture of separator, where you can have a very clear idea about the structure of the separator. Okay, as you can see, there are these micropores, the size distribution of the pore, okay, and the average dimension of the pore represent one of the most important KPI for the separator performance. Okay, there are some new startups in Asia that found some strategy to produce a separator with very, very, very controlled and homogeneous pore size. Okay, and this for sure increase the battery cell performance, make the performance very homogeneous through the entire battery cell. And the problem for sure is the scalability from the lab scale to the mass production scale, and we will see what happens in terms of cost. The separator film has a very thin thickness. We are talking about from 6 to 20 microns. The thickness mainly depends on the manufacturing process, okay? For cylindrical cell like this, the separator is very, very thin. We're talking about 6 microns, okay, or 9 microns. In some case, somebody is going to use 12 microns. For this kind of prismatic cell, again, that is done by zip folding process that we see later on. Again, here the separator could be very, very thin, okay, even 12 microns or 9 microns. For this kind of battery, pouch battery, that is done through a lamination process, the separator must be quite thick, okay, so we're talking about 15, 20 microns. The reason why is during this manufacturing process, there are some processes that stress a lot the separator material. So the risk to use thinner separator material is to have some internal short circuit during the working life of the battery. So for safety reason, the battery makers are using very thick separator compared to the cylindrical cell. I think this is a very important slide that gives you a good overview for the separator technology and separator feature. As mentioned before, the main, the main components of the separator layer is polyethylene and polypropylene, okay? Or just polyethylene or just polypropylene or a combination of the two in a multi-layer separator. The manufacturing type could be wet or dry, okay? As you can see, there are some pros and cons, okay, that later on we are going to explain. And even the stretching, okay, process could be axial, uniaxial, or biaxial. The stretching process is the process that allows to obtain the microporosity or the nanoporosity inside the separator, because there is a system that stretch the material and then the fiber, okay, and this creates the porosity, okay? So we can say that the stretching process is the most important process, one of the most important process in the separator manufacturing. In terms of manufacturing cost, the wet process is the most expensive, okay? And the dry is less expensive. We can say even that the PE is more expensive than the PP material. But I think the most important feature are this one: the shutdown function, meltdown temperature, tensile strength, in the two different directions, okay? So transversal direction and main direction, and resistant to the puncture, okay? We are going to analyze all of them one by one. The shutdown function is the property of the separator to disable the lithium-ion transition, we can say, flow, the lithium-ion flow through the separator, okay? So once the separator reaches a certain temperature, there is one compound inside the separator that closes the pores, okay? So once the pores are closed, there is no way for the lithium ion to pass through the separator membrane, okay? This is called shutdown function, okay? And is characteristic of PE separator. The reason is the PE has a meltdown temperature that is lower compared to the PP, okay? And this for sure could be a benefit, not to prevent the thermal runaway, okay? So what's happened? I think we can move to the next slide. Okay, let's move to No, okay. Let's stay here. What's happened if you have some failures in the during the working life of the batteries? The failures like a short circuit, okay, increase very quickly, as mentioned before, the internal temperature of the battery cell, and there are some passive system, okay, that prevent that the battery catch fire. One passive system is the separator itself, okay, because once the temperature start to increase, the one of the components inside the separator start to melt down, close the pore, and this block the lithium ion flow. Okay, so there's no more voltage in the battery, and this is called shutdown function. The shutdown function is related even to the meltdown temperature. Okay, so for very high meltdown temperature, sometimes it's very difficult to have the shutdown function because it's too much close to the thermal runaway temperature. Okay, the idea, okay, the best practice, as I know, is to have a shutdown function in terms of temperature, okay, just before the thermal runaway temperature, triggering the temperature. Okay, so the shutdown should happen just before the thermal runaway start in the battery cell. This for sure will prevent, or we can say minimize a lot the risk of thermal runaway. If the shutdown temperature is higher than the triggering temperature of thermal runaway, this could be a problem, because once the temperature starts to increase very quickly, there's no way to stop the degradation of the battery. Okay. To the other side, the meltdown temperature is another very important KPI, because if we have a thermal runaway temperature at, I don't know, 200 degrees, okay, and our meltdown temperature is at 120 degrees, that means that the separator degradation will start at 120 degrees, okay, and then we can have some failure, we can have some shrinkage due to the, failure due to the shrinkage of separator, because with the temperature, you don't know what happened to this separator. Maybe you create some shrinkage effect and uncover the anode to the cathode, and this way the anode can touch the cathode and make some short circuit. But for sure, if the meltdown temperature of the separator is very, very small compared to the thermal runaway temperature, you cannot use the entire working temperature range of the battery cell, because are limited by the melting down temperature of the separator itself. The other two important KPI are the tensile strength. Okay. The reason is related to the manufacturing process, some manufacturing reason. During some manufacturing process that we're talking about later on, and we are going to talk about later on, we're going to stretch the separator, okay, or to apply some tension on the separator during some manufacturing process, okay. If the tensile strength in the main direction or in transversal direction is not high enough, okay, what could happen is that the separator is going to decrease the width. Okay, so let's assume that this is my separator and I pull in this direction. Usually with a solid body, if I apply a force in this direction, the width decrease, okay, due to the Poisson effect. So if the width decrease, I can uncover the anode with the cathode. The anode and cathode can be in touch and create short circuit. Else, if my tensile strength in the main direction is not very high or is not sufficient, if I apply some tension on the separator during some manufacturing process, I can change the separator properties, physical properties. I mean, I can change the thickness, I can change the porosity in terms of size, in terms of distribution. This for sure will have an impact on the safety, because if I have thinner separator, this could be a problem. But I can even have a problem in terms of performance, because I don't have any control in terms of porosity. So even the lithium ion flow change from the nominal condition. And maybe I have some separator area with the very big pore and separator area with the very small pore. So the properties are, the performance, the electrical properties of the battery cell are not uniform now through the battery cell itself. As mentioned before, the thickness is very important, because we need to consider that we can have some particles on the electrode surface, we can have some cutting bars, we can have some debris, some contaminants that during the working life of the cell can touch the separator. I mean, these contaminants are very, very hard particle, okay, and can create a micro hole in the separator, and in this way this particle can make in communication anode with cathode and make some short circuit. Okay, so if the thickness is thick enough, okay, we can say, to prevent that the particle, the contaminants, pass through the separator, there's no risk to create short circuit. But again, it's not possible to have a super thick separator, because the separator is not giving any benefits in terms of energy density. Okay, its only function is to insulate anode from the cathode. Okay, so if we have in our cell a big volume represented by the separator, this volume are not giving us any cell capacity, any energy. Okay, so we need to find a compromise between separator properties, separator thickness, and safety. Then resistance to puncture, as mentioned before, is very important, because we need, the separator should be very, very resistant and resist to any sharp and hard particles present on the electrode surface. Otherwise, these particles can create some micro hole and then triggers some short circuit in the battery cell. This is an overview that help us to classify the separator characteristic in characteristic that can affect the, or can be taken in consideration for cell production, for the cell performance, for reliability and life, or for the safety. Okay, the shrinkage feature must be taken in consideration for the cell production, for the reliability and life, and for the safety, because again, if my separator tend to have shrinkage effect, that means that inside the battery, I don't know if you, let me check. Okay, you can uncover the anode with the cathode, okay, because maybe the separator makes some shrinkage, and then you expose the anode and the cathode, and you can create some short circuit, and this is not good for the batteries. Okay, but this can affect even the cell production, because when I mean the cell production, I mean shrinkage effect could be occur during the drying process. Okay, or during other process where the cell goes into very high temperature process. Okay, so in this case, the separator can suffer of shrinkage and then create some problem in the downstream area of the production. The modulus, we already mentioned before, can affect the cell production, because if in some manufacturing process I need to apply some tension of the separator, very high modulus can keep the separator properties very homogeneous. Not high modulus are not able to keep the separator properties homogeneous. The drying temperature is another important KPI for cell production, even for the reliability and life, because if the separator cannot be dry at high temperature, this creates some shrinkage. This maybe this trigger the shutdown effect. Okay, and even can create a degradation of the separator itself. So since the separator should be dry for the cell manufacturing, it's important to consider the drying temperature with the characteristic temperatures of separator. Then we move to wettability. That is important for quite everything except for the safety. So it's important for cell production, cell performance, reliability, and life. The wettability is the capacity of the separator to be wet by the electrolyte. The electrolyte goes into the separator porosity. Okay, if the separator is wet completely and in homogeneous way by electrolyte, during the formation that we see later on, we will have a very thick and homogeneous solid interface layer, okay, of electrolyte. And this allows to have even very homogeneous performance through the battery cell. And even have a reliable product, okay? Because we can measure the performance during the working life and we can understand what's happened. Thickness in terms of cell performance, but we can say that it can affect even the safety for the reason that I mentioned before. The weight, again, mainly cell performance, because weight and thickness are in some way correlated, because if the thickness of the separator is very, very high, this can decrease the overall energy density, volumetric energy density of the battery cell. To the other side, if the weight is very high, this can decrease the energy density of the battery cell, the graviometric energy density of the cell. The ionic resistance affects the cell performance because the ionic resistance of the cell, so the resistance at lithium ion flow, affect the performance, because with high ionic resistance, the ion cannot pass through the separator very easily and very quick. So we cannot have a power battery cell, but maybe in this case we talk about energy battery cell. And the very high ionic resistance can even increase the temperature inside the battery cell during the working life. And again, the porosity, for the same reason, is very correlated to the ionic resistance sometimes. And we spoke about it before. And then we have the penetration resistance and meltdown resistance that are two important KPIs for the safety, for the reason that I mentioned before. Maybe I come back to the previous slide to explain you a little bit more about the puncture strength. Let's assume here, okay, this is a cross section of the cathode. Let's assume that one of these particles, okay, remain on the cathode surface through the entire manufacturing process. At the end of the manufacturing process, over this cathode surface will be a separator layer. And over this separator layer will be an anode, then separator, cathode, separator, anode, and so on. Everything stacked to each other and compressed to each other. So this particle, that is a coating particle, apply a certain pressure, local pressure on the separator with a certain force. If this force is enough to pass through the separator, this cathode will be in touch with the anode that is to the other side of the separator, and this creates a short circuit. Okay, and these are very, very bad things, because this can start the degradation effect, the thermal runaway, and your battery can get fired. So this is the reason why the puncture strength is very important. Okay, so here there is explanation about what we talked before. I just forget to mention about the ceramic coating. Okay, usually the separator, in order to increase their electrical resistance, are covered on both sides or just one side with the ceramic coating that usually is alumina, okay? So is aluminum oxide. This for sure increase a lot the electrical insulation of the separator, so increase the safety, okay? And don't have a lot of effects in terms of ionic resistance, okay? So, but for sure increase the cost of the separator, because instead of have just a pure polymer film, you need to add even the ceramic coating that is a very, very thin layer. I mean, something like 1 microns or maybe less. That for sure increase the price, increase the complexity of the manufacturing, but increase the safety. We can say that 95% of the cell maker are using currently separators with the ceramic coating, at least on one side of the separator membrane. Okay, here there is a slide that represents the performance of different separators. Okay, so there is the polyolefin membrane like PP and PE, nanofiber separator, ceramic filled no woven separator, coated PO membrane, that is the case of polypropylene and polyethylene with ceramic coating. Okay, so if we focus on the yellow and the blue lines, we can see that we have high porosity, okay, for the polyolefin membrane coated by ceramic coating. The reason why is they can allow, the separator makers can allow bigger pore size, okay, without losing in safety, okay, because there is their ceramic coating that increase the electrical insulation. Indeed, as mentioned before, this doesn't change the ionic resistance, okay. I mean, yeah, no, increase the ionic resistance a little bit to the ceramic coating layer, but not a lot, and more or less have the same properties. The main problem of the polyolefin membrane without ceramic coating is that it's very sensitive to the temperature. Okay. As you can see, the score for shrinkage, meltdown, and drying temperature is very, very low. And the reason is because there is no ceramic coating layer that increase the resistance at the temperature. Okay. So this is the reason why many players are moving from PO membrane without ceramic coating to PO membrane with ceramic coating. Currently, there are some studies regarding the no woven and the nanofiber separator. As you can see, no woven and nanofiber separator have a very good, very great property in terms of meltdown, shrinkage, wettability, good property in terms of ionic resistance, and even for the other, okay, KPIs. The problem is that seems not possible, okay, to achieve very thin thickness and very light separator for no woven and nanofiber. This is the reason why the score is lower compared to the PO membrane, but is quite similar to the coated PO membrane. Anyway, based on some studies, seems that still quite difficult to obtain the nanofiber, the non-woven separator in very cheap way for the mass production. But I think the reason is just because we are in the early stage of the developing. So the non-woven, the nanofiber could be the next generation of separator. Have all featured to be a very successful idea for the separator material. The problem is just the manufacturing cost. Okay, so as you know, one of the targets is to decrease the cost per kilowatt hour, and mainly the cost is represented by the the materials of the battery cells, so anode, cathode, separators, and so on. In terms of global separator demand, I mean, even here is quite obvious, the separator demand is going to increase very, very rapidly with the lithium-ion batteries demand, okay? There are some not many companies for separator manufacturing. Most of them are in Korea and China, okay? So are Asian companies. The main one are Semcorp, Toray, Asahi, and Skiet and Senior, okay? Toray, Asahi, Semcorp are the one that are most used by the main battery maker. And even their expansion plan even for them, there are some expansion plan, especially for Toray and especially for Asahi. Semcorp is going to invest some billions, but not like Toray and Asahi. But again, the trend is like the same for the cathode and anode material. Here there is other separator suppliers. I mean, this is quite the entire list. As you can see, there are some companies that are battery cell maker that are producing internally even the separator. So one is LG Chem, one is Panasonic, one is SK Energy, and one is Samsung SDI. What to say? Panasonic is a Japanese producer, LG Korean, SK Korean, and Samsung Korean. The only difference is that right now is not LG Chem anymore, but it's called LG Energy Solution, the business unit of the batteries. For Panasonic, LG Energy Solution, Samsung are the same business unit for batteries and separator. For SK, separators are produced by SK Energy and battery cell from SKI, that is SK Innovation. But yeah, as you can see, most of them comes from Asia. Okay, then we have the electrolyte. As mentioned before, the electrolyte is a mix of lithium salts and organic compounds, okay? The lithium salts will dissolve in the organic compounds and dissolving release the lithium ions that are able to flow through the separator, okay? The electrolytes have some KPIs as well, okay? One is the wettability, low viscosity, low adhesion angle, and high surface tension. All these KPIs allows the separator to be soaked by the allows the electrolyte to be soaked by the separator. Okay, so the separator must be able to be wet by electrolyte. So in order to achieve that, the battery maker can work on the separator design, but need to work even on electrolyte design. The organic compounds are usually EC, PC, EMC, and DMC. The base is carbonate, and again is ethylene, propylene, ethyl methyl, or dimethyl carbonate. So are aromatic compounds usually that are toxic, as you know.